Hello. Oh, I want you can hear us. What happened? Arun, you can hear us?
Yes, yes, Aramshita.
Okay, thank you. You can mute yours. Hey, push.
Hello.
I think we can start. Okay, to celebrate the International Year of Science and Technology, we have been organizing a series of colloquiums at Secure. And first speaker was Professor David Wineland, a Nobel laureate. Our fourth speaker is Professor Archan Majumder from SN Bose National Center for Basic Sciences. Professor Majumdar obtained his PhD from University of Delhi in the area of general relativity and cosmology. Just at that time, this field of quantum information was emerging. So he got this quantum bug like a lot of other people. And since then, he has been working in both areas, quantum information as well as general relativity and cosmology. In quantum information, I think his major area of interest has been uncertainty relation, steering inequalities, as well as witness operators. So today, I think he's going to tell us about some of those areas, you know. So I just Professor.
Yeah. Thank you, Pankaj, for the nice introduction. And it's a great pleasure for me to be here. And today share with you, some of the works that we have been doing for the last 15, 20 years. How much time? It's a 1 hour talk or 1 hour talk? Okay. So, and it's also the honor for me to speak at this forum where you are celebrating the 100 years of quantum mechanics. And there have been several illustrious names, as Pankaj pointed out. And to be in their company is really an honor for me. And I would again like to thank the organizers for inviting me to give this talk here. So today I will be speaking generally on the topic of quantum uncertainty relations, and some of you students might wonder, this is an old topic, again almost 100 years old. So what is new about it? The new elements that I would mention is some of them, the formal developments in uncertainty relations are not exactly new. They happen continuously after Heisenberg's principle. But the applications in information science, a number of new interesting applications in quantum foundations and quantum information, that will be the focus of my talk, applications of uncertainty relations. Okay, so what is the perspective of today's talk? The perspective is that after all, quantum mechanics, as all of you know, is one of the most important founding pillars of modern physics. And it came about in the early 1900s. And essentially, the departure from existing physical theory was qualified by two elements, two major elements. One of them is the uncertainty principle, and another, in some people regard as the superposition principle. And these have no analog in classical particle mechanics. Okay. So this brought about the so-called first quantum revolution, and all of us are actually, I mean, enjoying the fruits of this first quantum revolution. And things like, say, early on, I mean, transistors to today chips and lasers, etc., would never have been possible, all technology, without quantum mechanics. So that is essentially called the first quantum revolution. However, something happened almost, say, more than 70 years after the development of quantum mechanics, and that was amalgamation of some quantum foundational issues with information theoretic principles or information science. And this development started from the late 1990s. Does the cursor work? Never mind. Okay. And this has brought about the potential for entirely new quantum technologies, and not only potential. Today, we do have elements, at least starts of these technologies, and some of them you people are also doing. Okay. For example, you have a wonderful quantum computing lab, which Professor Upende was just mentioning. So this wouldn't have been possible without applications of quantum information. Okay, so the uncertainty principle, essentially, I have written down the Heisenberg uncertainty relation, so everybody knows about it. And there are two kinds of way how one can view this uncertainty principle. And one is essentially the Heisenberg, the original, I mean, thought of Heisenberg, that if you measure a quantum mechanical observable, for instance, the coordinate or position of a particle x, then its momentum becomes uncertain, vice versa. So this has to do with measurement, the essential disturbance in a quantum measurement, and the error associated with inference of another complementary variable. However, apart from this historical fact, in most of the history of uncertainty relations have been to do with preparation uncertainty, the so-called preparation uncertainty. And what does it mean? It means that there exists a fundamental limit to which certain complementary observables or variables like position and momentum can be known. Okay, so this has per se nothing to do with measurement or error and disturbance. So if you have a quantum state and which supplies you the maximum amount of information that you could gain in quantum mechanics, that is allowed by quantum theory, then there is indeed a fundamental limit to the precision regarding which precision about either one of the observables or the other. Okay, so this is quantified in terms of the uncertainty relation. And in order to ascertain, I mean, what kind of precision we have, we are indeed led to mathematical inequalities. One of them is the original one which Heisenberg wrote down, and there have been many developments which I'm going to point out. And these inequalities can be verified in a lab by performing a series of measurement on identical states of particles. Okay, by the way, please feel free to interrupt me because this is a colloquium and I would like to go ahead only as far as I can make sense to the audience. So if anybody, particularly young students or anybody else has any questions, please feel free to interrupt me. Okay, so now the talk, what I'm going to speak, not just the uncertainty relation or relations, but their applications to quantum information science. So to begin with, this is a nice place to define what is quantum information science. By the way, this is a very heuristic definition. So it can be put in a nutshell that quantum information science is the theory and practice of accomplishing physical tasks that are not achievable using laws of classical physics. Okay. And this has to do with storage, transfer, and manipulation of information which is contained in physical degrees of freedom of elementary particles which are governed by quantum mechanical rules, right? And at this day and age, all of you know about many examples. For example, you have secret quantum key generation, quantum cryptography, quantum computation, quantum teleportation, so on and so forth, right? So there are many aspects of quantum information. And one of them I particularly like is teleportation, only because I've worked in teleportation. And again, all of you know what is teleportation. It is the art of sending an unknown original state to a faraway location without physically transporting the quantum particle. And in that, the resource of an entangled pair of objects is required. Okay, so if you generate a pair of entangled particles, one of them goes to this side, party A, and party A has the original state which he or she wants to transfer to party C. And then by making some measurements, combined measurement or joint measurement on the particular shared entangled pair, and the original state, and then conveying some classical data to the other location. Party C can apply some treatment on his or her particle and then get an exact replica of the object A. And by the way, in quantum mechanics, we also have a famous no cloning theorem that says that you cannot exactly clone the state of a quantum system. So when I'm saying a replica of object A is formed at this location, then the original has to be destroyed. This is fundamental in quantum mechanics. Okay. So teleportation earlier on 20, 25 years ago, people used to make fun. People thought it was a matter of science fiction. Now it is no longer. And lots of labs, several labs around the world have implemented it, including in India. And these days, one can also implement teleportation from the Earth to an artificial satellite. That is what at least 2 or 3 countries have claimed so far. Now, why is teleportation? Teleportation is, of course, very interesting, but it is also of a lot of use as far as future quantum applications are concerned. And this is to do with distributed quantum computation. And whenever, if you have any day, you have a quantum internet, then teleportation will be essential to such quantum networks. And I would just refer to an old work of ours 15 years ago, when we showed how such quantum teleportation can be ascertained, or we can know for sure, suppose you have an unknown state, whether it is useful for quantum teleportation or not. We showed that this can indeed be possible by the method of witnesses. So Pankaj somehow actually, foresaw maybe that I like witnesses. So he said that this is something related to witnesses. But you can actually witness quantum teleportation using this method. And again, I would like to highlight that this has been applied in several places, and this particular method, and one of the areas of application is boson sampling. Okay, so the main point of this presenting this slide here in today's talk is that teleportation which is a wonderful application of information processing. It is not just, important or interesting from a fun point of view, but it has immense application in future quantum networks. Right. So this is the introduction, and the essence of today's talk is linkage of quantum uncertainty with quantum information processing, and this is the plan of what I'm going to speak about today. So what I'm going to basically convince you that a lot of us, even when I got into this subject, I did not know that apart from Heisenberg uncertainty, there is something else. But after the formulation of Heisenberg uncertainty relation 100 years ago, there have been many further formulations, starting from the immediate work of Robertson and Schrodinger. Then there have been other kinds of variance-based relations. There have been entropic versions, coarse grain, fine grain versions, so on and so forth. And most of these uncertainty relations have many different kinds of applications, and some of them I will be highlighting today. For example, determining the purity or mixedness of a quantum states, and demonstrating EPR paradox, which is one of the most fundamental aspects in quantum foundations, right down to quantum steering. Then applications in quantum memory, then quantum key generation, so on and so forth. So this is going to be the plan of my talk. I would take one particular example from here and show how it would be interesting for quantum information processing applications. Okay. So let us start with something which is there in a textbook. So this slide, I would show everything together. By the way, don't get put off by this kind of mathematical jargon or derivation. Let me promise that this is the only mathematical derivation that I would give in this colloquium talk. So this is textbook material. So if there is uncertainty in a quantum mechanical observable A, you can quantify it through its variance. And this is immediately proved in textbooks. Suppose you have two self-adjoint operators and you take a combination A plus I lambda B, A minus I lambda B. Lambda is an unknown parameter, and you try to minimize this with lambda. Of course, the way I have written them, the product expectation value is, of course, by definition greater than 0. If you minimize it, then you will get a value of lambda. And what is that? It is nothing but the commutator of these two self-adjoint variables. Okay. And now you plug back the lambda in, and what you get is the product of the squares of these variances greater than or equal to minus 1/4 expectation value of the commutators of these two variables. Okay. Now immediately you see that in quantum mechanics you have certain things called pairs of observables. The primary example you learned is position and momentum, and for those kinds of observables, you get this. So you have their commutator equal to IH cross. Okay. H cross is the Planck's constant divided by 2 pi, and you immediately get the Heisenberg uncertainty relation. So it is a very simple, elementary, back of the envelope textbook definition or textbook calculation. So this is something very concrete, very firm. So what is the need of going beyond it? That is the main point, right? So before doing that, let me just talk about one application. If before going beyond this Heisenberg, this elementary textbook stuff, to other kinds of quantum uncertainty relation, let me again talk of one application in quantum foundation of this uncertainty relation, and that is to do with demonstration of the EPR paradox. Now, EPR paradox, again, people, I mean, some of you must know about it. It was something when Einstein and his two collaborators wrote, it made a huge impact because Einstein was one of the founding forefathers of quantum theory, but he was very unhappy about it, right? So this was in the year 1935, and Einstein posed some argument by which he tried to claim that quantum mechanics is not a complete theory. There is something missing in our understanding about it. And the essence of this demonstration by Einstein is to talk about a joint state of two particles represented by the single wave function psi. And such a joint state of particles is characterized by the property that two particles can originate and they can move further apart, but the state remains unaffected. So that is the key element of this. And this brought about a lot of, for example, a lot of press reports, Einstein attacks quantum theory, and so on and so forth. So again, very sort of heuristically, I mean, what is the slide? Okay, now we have it here. Yeah. So this is the famous 1935 paper, and it is one of those papers which still creates a lot of debate in the community. Okay. But the debate per se may not be very relevant for what I'm going to say, speak now. But just to key you in with this, I mean, essentially, what is the idea of this Einstein Podolsky-Rosen paradox? EPR considered two spatially separated particles with maximum correlations in their positions and momenta, right? All of you appreciate that. If two particles that originate from a they can have correlations. And in this, okay, and then EPR assumed two facts about physical theories. And one of them was that there is indeed something called locality, because Einstein anyway was very fond of, he founded the special theory of relativity, which is based on the idea of locality and spatial separability. And that another way of saying it is it actually leads to the fact that there can be no action at a distance. Everything can propagate from one place to the other, not greater than the speed of light. So this is one of the assumptions he made. And the second assumption Einstein made about the nature of physical theory was something called reality. And here I would exactly quote what was written in that paper. So what is reality? It says that if without in any way disturbing the system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this quantity. Okay. So these two definitions, according to Einstein and his collaborators, appeared perfectly logical and rational for any physical theory to possess. Okay. So now EPR applied these two results or these two assumptions on a special framework or special setup of two particles which are correlated but which are not interacting as of now. Okay. So then what happens? Since they have correlations in position and momentum, and because momentum is conserved, there are no forces acting on this particle, then what happens is that you can easily see that if momentum is, the overall momentum is conserved, suppose the initial state had zero momentum, then if a particle moves to the left, other to the right, I can pinpoint, if I measure the position of one of the particles, I can immediately pinpoint what the position of the second one will be, right? Now I can similarly again apply the same logic, zero momentum. So the particle on the left, if I measure some momentum, I can infer that the particle on the right will have exactly equal in magnitude but opposite in. Now, as soon as you do that, then what you say is that therefore by this logic, you say that there is a definite predetermined value of position of particle 2 without even disturbing it. And similarly, therefore, again, a definite predetermined value of momentum of 2 without disturbing it. Okay. Now, this leads to a very, extreme paradox and a conflict with what? With the uncertainty relation. Why? Because in quantum mechanics, you know that no particle can be in a definite position of both the canonically conjugate pair of observables, right? So it conflicts the uncertainty relation, and therefore, so since no state in quantum mechanics has this property, therefore we are led to following uncertainty relation. So we are led to some paradox, and Einstein considered that the theory is incomplete. But as I said, let us not go towards that track. But today I would like to tell you how this paradox has been essentially revealed in experiments which are 50 years later from the Einstein-Podolsky-Rosen paper. So this was in 1935, and a group of Margaret Reed et al. In 1989 first showed how this could be demonstrated, and they instead of considering position and momentum, they considered quadratures of two correlated and spatially separated light fields, because you could do experiments easily with light fields. And one could write down the correlations, and by measuring one of these quadratures, you could infer the value of another one. And in doing so, you are led to a apparent contradiction with the Einstein, with the uncertainty principle. However, again, be very careful. There is absolutely no contradiction. Why? Because I am writing the same form of the uncertainty relation for inferred variances. By delta INF, I mean variances that are inferred by not measuring the quadrature, but by measuring something else. And what is that something else? It is another quadrature which is correlated with this one. Okay. So this is a violation of the inferred relation. So there is no real uncertainty relation violation. Nobody in physics has ever violated it. That is why they are sacrosanct. But because I'm doing so, I can immediately test it in experiments and prove that the EPR paradox exists, and that is what these people did, Margaret Reed et al. They calculated these inferred variables, and lo and behold, that this was violated, and so therefore they concluded that the EPR paradox is indeed revealed in quantum mechanics. Okay. So what is the point of this? Again, as far as the relation with my talk here, that this is a basic principle of quantum foundations, and after all, as I said in the original slide, all quantum information starts with quantum foundation, study of quantum foundations, and there is an immediate application of the Heisenberg uncertainty relation. Okay. So now let me move on to other versions, next versions of uncertainty relation, and by that, and what is the need? So that is the point. So first of all, look that you are quantifying uncertainty in terms of variances or standard deviation, right? So this is the Heisenberg uncertainty relation. But there can be situations where the variance vanishes. And what it could be, what type of situations? For example, you consider states that are eigenstates of these observations, right? So in eigenstates, you immediately, if you have an eigenstate, you measure, you get the eigenvalue. So where is the, variance? There is no variance. So in that case, you get a very trivial relation, 0 greater than or equal to 0. So uncertainty relation in the Heisenberg form is not useful at all, right? If you want to quantify the nature of uncertainty which exists in such states. So this is one of the point. And there is people realize immediately after Heisenberg wrote this, relation, people like Robertson, Schrodinger, etc., they realized that there is much scope of improvement. Because first of all, as they said, that the bound which is given by the right hand side, which is the expectation value of the commutator of these two variables, is not an optimal bound. Okay. So we will come to it later why it is not an optimal bound. And also, this is measured the expectation. If you want to measure the expectation value of something, it has to be with reference to a particular quantum state, right? So this is again a state dependent bound. It is not a state independent bound. So that is another problem. Okay. So two problems. And what is the third one? The third one is as follows. So here I am using variance. Variance is, after all, if you look into it in terms of moments, okay, it is the second order moment. And there could be quantum states, particularly those of you who have learned about continuous variable states of light. There could be many quantum states, many interesting quantum states, especially non-Gaussian states, where the full information or quantumness or resource of the state is not captured at the level of second order moments, right? And for such states, variances indeed does not fulfill what we want, right? And so on and so forth. There are many other problems, many other issues. For example, if you consider mixed states, you have other issues as well. So therefore, this led to people like Robertson and Schrodinger to propose various tighter relations. Again, to begin with, this is the Robertson-Schrodinger form of the uncertainty relation. They also use variances, but in the right-hand side, on the right-hand side, in addition to the standard commutator, if I put this here, if I put it to the right-hand side, now I've put all on the left-hand side, you will see that there is another term. In particular, there is also an anti-commutator of this two observables. Now, even if you have commuting observables, you will see that this anti-commutator will lead to a certain term. If you put it on the right-hand side, a positive term which will make the bound not zero, but something higher than zero. Right? Okay, and this is very easy to derive such a relation. Of course, again, as I promised, I won't go into the derivation. If somebody is interested, we can talk about it. This is just the application of the Schwarz inequality, nothing else. Okay. So one could apply the Schwarz inequality and get this Robertson-Schrodinger form of the uncertainty relation, which is tighter compared to the Heisenberg uncertainty relation. Why? Because in addition to the commutator, which are labeled by C, you also have such anti-commuting terms. Okay, so now what is the, as I promised that I wouldn't talk of any uncertainty relation without any implications in quantum information. Now I would talk of another implication, that is discriminating between pure and mixed states. So all of you know what are pure and mixed states. So the pure state is described by a single state vector, and there exists complete knowledge of a state. However, in most practical situations, there is lack of knowledge. Why? It could come about due to many factors: imprecision in measurements, interaction with environment, so on and so forth. And you do not have access to all degrees of freedom. Of course, if you have an environment, it has too many large degrees of freedom. So you lose access to that. So therefore, you end up with mixed states. Okay. Now, mixed state description is in terms of the density matrices. And then the question is that if you have a mixed state or a pure state, then naturally the performance of these two differ with respect to many kinds of things. For example, you want to apply a quantum state towards quantum computation. As soon as you have a mixed state, the performance will, in most cases, decrease. Of course, there can be some special cases also, and so on and so forth. So it is of utmost importance to know whether a given state is pure or mixed. And how do you know it? Of course, since initially I talked about teleportation, therefore I have given this picture. So in quantum mechanics, in order to discriminate one type of state from others, you typically try to prove that a set of such states is convex and compact. But in this case, it is not possible because the set of all pure states is not convex. So you have to find other methods. And one of the such methods is application of the Robertson-Schrodinger uncertainty relation, as again we did about more than 12 years ago. So what we did was we took this I and a few of my students, we took this Robertson-Schrodinger uncertainty relation, and we chose operators A and B such that for pure state, this expression on the left-hand side, it is exactly equal to 0, whereas for mixed states, it is positive definite. And the interesting thing is that, at least for certain kinds of states, that is qubit states, one can choose Q in such a way that it exactly is equal to the linear entropy. And those of you who have learned a little bit of quantum information know that linear entropy actually quantifies the mixedness of a quantum system. Okay. So this is a very simple way of doing it. We choose these two operators as nothing but, projections of Pauli spin operators. Very simple. Okay. So you get Q as the linear entropy. Now, using this, we were able to classify a large, category of states, qubit states, single party as well as two party. Now, of course, we can't classify all kinds of states you can think about. And why this is so? I just told you the answer 2 or 3 slides ago. Remember, I said that we are using this Robertson-Schrodinger uncertainty relation. And in what sense it is similar to the Heisenberg uncertainty relation? Again, we are quantifying uncertainty in terms of standard deviation or variance, right? So again, when will this way of classification fail? Whenever your property of the quantum state is such that it is not captured at the level of the second moment, standard deviation or variance. So therefore, our method fails for those kinds of states, right? Okay. So then again, we think of further scope of improvement, because as I said that this is uncertainty is measured by standard deviation. And another thing which I also mentioned earlier is that again you compute this right hand side, whether you compute the commutator or the anti-commutator, it is some expectation value of that on a particular given state. So all of these are state independent forms. So can we do anything better? Okay. So, and there are examples of other variance-based relations, so which I would briefly mention later. So the question is, can we do something better? And the answer is yes. So instead of choosing just one moment, 3 moments, we can actually insert in a way a combination of all moments, and that is captured by what? The entropy function. So again, so this is the entropic uncertainty relation, and as promised, again, I will not go through the mathematical derivation. It is also not very difficult. So if anybody is interested, you could ask me. So then what we end up is the relation not on variances, but something called Shannon entropies, okay, of observables A and B, okay, and we get a right hand side which is log of C. Now, what is this right hand side? So that is something interesting. So the right hand side is nothing but measured in terms of probabilities of observables, okay. So suppose you have a quantum state, you can make 2 measurements. The simplest possible case I'm telling you, this is a qubit state, and these are 2 directions, okay, of Pauli matrices. And suppose these measurements are dichotomic, you can get 2 variables, A and B, right? So then the probability of getting this A is given by, say, PA, and B is given by PB, and the average uncertainty is nothing but P log P, right? So this is indeed 1 by C, okay. So in other words, what is this bound? What is the right hand side? The inverse of it. It is the maximum possible overlap of these 2 probabilities, 2 different ways of measuring this system in 2 different directions, maximum possible overlap in any given quantum state. So now I'm calculating the bound by using the actual probabilities of getting these outcomes. Okay. So 1 by C therefore quantifies the complementarity of these observables, because if these observables exactly overlap, then what is PQ? This is 1, right? And you have log of 1, that is 0. So if they exactly overlap, that means you are measuring along the same direction, both of them. So therefore there is no uncertainty, right? Am I making sense? Suppose you measure an object along a direction, the state is forced to an eigenstate of that. Again, if you measure on the same direction, then there is no uncertainty, right? So therefore the bound is 0. So you have no uncertainty. But if they are orthogonal, then you have a maximum possible uncertainty. That is what we are quantifying here. Okay. So now, as promised again, so this is a very, a simplistic way of presenting the Heisenberg uncertainty or the entropic uncertainty relation. So now I would come to another application which follows from EPR paradox, and that is called quantum steering. Again, what is quantum steering? This is also an idea, is again very old one. This came about due to debates between Einstein and Schrodinger. And so Einstein actually thought that this kind of the EPR paradox means some spooky action at a distance. He was not happy. But Schrodinger was the one who, even in those early times, realized, although he was not comfortable with it, that this means that there is quantum correlations in principle, and these are stronger. I mean, they are very strong. They are stronger than classical correlation. So that is what Schrodinger said, and Schrodinger in his response to the CPR paper made some very, visionary statements, right? And one of the most visionary statements he made about entangled states or inseparable states or correlated states is the fact that the best possible knowledge of the whole is not necessarily the best possible knowledge of its parts. It's not necessarily the sum of best possible knowledge of its parts. So if you have entangled state of two particles and you are trying to infer knowledge of the state by measuring these two particles locally at two separate places, and you collect some information and add them up, you don't end up getting the best possible knowledge of the entire quantum state. This is very important. And the other thing, so this is a characteristic property, the characteristic property of entangled state, right? So they are inseparable in the true sense. And the other most important thing which Schrodinger actually pointed out, although he found uncomfortable, is that this theory allows a system to be steered or piloted. So if there is an entangled state and you are making a measurement on one component, that means you're automatically steering the state of another component, which may be very far from you. But again, be very careful. We are not violating any laws of relativity because no signal is traveling faster than light. Okay, so EPR paradox, another way of looking at this EPR paradox is something called quantum steering. So suppose you have the state of two systems and they are in a joint state, and to now assume that they are not pure, but they can be mixed also. So there can be many possible ways, actually infinitely possible ways of expressing these states, okay? Depending on what? Depending on what kind of basis states you choose. So here I've chosen two basis states, set of states labeled by UN and VN, okay? So now suppose these two particles are there with two distant parties. One of them is Alice. And if Alice chooses to measure in this state, set of states UN, then she instantaneously projects both system to one of the states psi n. Why? Because here the state is composed in such a manner that as soon as you take out one component of UN, you get a corresponding matching component of psi n. On the other hand, if Alice were to choose to her basis not as UN but as one of the states VN, then what will happen? Pop state will be projected to not one of the states psi n but one of the states phi n. So essentially this captures what is called quantum steering. Now the idea is very old, but this people knew about say 70, 80 years ago, but just about 15 years or so ago, Weizmann actually pointed out that this is indeed not only fundamental, but this can be tested, again measured in the lab, and it can have tremendous application. So what they did, they gave a mathematical formulation of quantum steering. And those of you know, actually I'm jumping too far ahead, that the entanglement or non-locality that I talked about, it also has a mathematical formulation. Have you people heard about Bell inequalities or Bell type inequalities? Some of you may have heard. So exactly similar to such Bell type inequalities, one could have steering inequalities. And you could measure them, you could quantify them, and you can test quantum steering in a lab. So this is a typical, cartoon from a paper in Nature Physics after 2010, again by the group of Weizmann et al. In collaboration with certain experimentalists. And they assume again two parties which are far away from each other. And Alice is supposed to reside in a black box. We do not know, we do not trust Alice, what she can do. She can be very truthful, she can also cheat. But the essential point is that in one of her trials, she could send say a pair of entangled particles. Okay, or somebody else could prepare a pair of entangled particles, send one to Alice, the other to Bob, and both of them can make measurements, and depending on their measurement choices and outcomes, they can actually write down, they can compose this mathematical inequality. Nothing but expectation value. Now the whole thing changes if Alice, instead of using a one party of a pair of entangled particles, just cheats and send a pure state to Bob. In one case, you will violate such an equality or inequality, you will have quantum steering, and in the other case, you will not, right? So this could allow you to experimentally demonstrate quantum steering. And again, as with teleportation, it is not a theoretical curiosity of we people doing foundations are interested in, but this has tremendous applications in what? Quantum cryptography. I'm going to come to that later. Okay, so before we move on to further applications, let us go back to variance uncertainty relations. And even at the level of variances, you could do something more than what the early forefathers did. And you consider the variance delta S square delta V square, but instead of taking the product of these variances, you take the sum of these two variances. And therefore, again, in the right hand side, instead of just the commutator, you have another term. So this again tightens the bound, right? And as I said that once you do it, then where is the application? So this application was again found a few years after this paper by Makun and Pati. So we showed that again one could demonstrate a different form of steering. So this is now called Einstein-Podolsky-Rosen steering, using such some uncertainty relation, which essentially tighten the bound. So we can demonstrate quantum steering, which is better than demonstration using the Heisenberg uncertainty relations. So this is another application. So now the question is that why do we, need to go far and far, further and further better. So this is sort of repetition of what I'm trying to emphasize. So the EPR paradox, as I said, was first demonstrated by Reed using some inequalities, which were typically obtained or written down in context of quadratures of light fields. Okay, this is the one, inferred variance of observers. Now the question is, again, I'm repeating it, that there indeed, as these people saw, who Reed et al. And also later others, that there exist certain continuous variable states which do not violate such Reed inequalities. Okay. So therefore, why they do not violate? Because their correlations may be hidden in higher order moments of observables, not up to second order. Now, so therefore, one could, instead of using this variance, one could use entropic functions again, right? This is natural, because we indeed have to our benefit entropic uncertainty relations, as I said. And again, I, in collaboration with Girish Agarwal and a couple of my students, did exactly this. This is also about 10 years, 10, 12 years ago. So we considered entropic steering inequalities and considered examples of states which do not exhibit such steering or EPR paradox using Heisenberg uncertainty relation. And one particular such state is Lagauer Gaussian beams. These are angular momentum entangled states. And such states actually do not exhibit EPR steering using the standard Heisenberg uncertainty relation. As you said, I can plot uncertainty. And if you increase this angular momentum number, this n refers to the angular momentum number. This is the first such one, 1, 0 of two modes. And you can go on to ij, and this n just represents that. If you go to higher modes, the uncertainty increases. But you still can't exhibit quantum steering using the uncertainty Heisenberg uncertainty relation. But instead, if we consider the entropic uncertainty relation, then you indeed get violation of that inferred uncertainties, and therefore you can do quantum steering with that. So am I making sense? Am I being clear? So if you have any questions at this stage, I would appreciate. Okay? Right. Okay. So now let me summarize what we have learned so far. So far we have considered or viewed several kinds of uncertainty relations. One is the standard one, the so-called original Heisenberg uncertainty. Then we have seen some improvements of it. Okay, Robertson-Schrodinger form. So here we have anti-commutator as well as the commutator. And such kinds of uncertainty relations have several applications. So I have told you about determination of purity of mixedness. One could also detect entanglement using this. And also this can be used as witness of mixedness, as I said. But again, to re-emphasize that they have these kinds of relations have certain drawbacks. That first of all, the lower bound is state dependent, and this captures correlations only up to the second order. So To do better, people introduced entropic uncertainty relation. That is also almost 50 years ago. The first formulation took place, both for discrete and continuous variables. And such entropic uncertainty relations have been used to detect quantum steering. Not only by us, actually, there were other papers also. These are the references. And another very beautiful thing, that is uncertainty relations in the presence of quantum memory. Okay. However, there is still a drawback of such entropic uncertainty relations. And what is that drawback? Because quantum entanglement leads to non-locality, and such uncertainty relations cannot truly reflect the amount or magnitude of non-locality. So we will go towards that. So therefore, this is the property of all coarse-grained uncertainty relations, which are based on measurement of what? Variances or entropic functions. So instead of using coarse-grained uncertainty relations, one could do slightly better, as was pointed out by Oppenheim and Wenner in this 2010 science paper, that you could measure uncertainty directly in terms of probabilities. Okay. And what they said, so in a fine-grained uncertainty relation, the uncertainty of a particular measurement or any combination of outcomes is considered, right? Precisely. So we are finding in the sense that we are not averaging over all possible outcomes, but we are considering a particular outcome or a combination of particular outcomes. And the uncertainty is then directly given in terms of measuring probabilities. And what is the advantage? One immediate advantage is that this will lead you to capture the exact non-local strength of quantum theory. Okay, so again, if you just focus on, forget other things, just you focus on this probability. So suppose something has only two genuine values, 1 or 0. Okay, so then if you get an outcome 1, we are certain about that. If we get an outcome 0, we are also certain about that. Okay, but suppose if the probability lies between 0 and 1, again, naturally, this corresponds to some kind of uncertainty, right? And in this case, we are exactly doing that. We are considering outcomes or combination of outcomes, and by measuring their probabilities, we are quantifying the uncertainty of a pair of physical variables. Okay, right. So we need not, sorry, what did I? Yeah, okay. So therefore, what I said was that the essential idea, so one would need it, but at the moment you can just regard as probabilities quantifying uncertainties, nothing more, nothing else. And as I said, that they can capture the strength of non-locality, so this can be proved, and again a lot of people did it. I'm only just reflecting, I'm being biased and reflecting our works, our students, again more than 10-12 years ago. So here what we did was we considered tripartite systems, and we showed that tripartite systems have something called genuine non-locality. And we showed that using such fine-grained uncertainty relations, we can capture genuine non-locality of such tripartite systems. Okay, so then now let me come to something else, which is again very beautiful, that is uncertainty in the presence of quantum memory. Now, what is quantum memory? Okay, so suppose you have a party here, okay, Bob, who has a quantum state with him. But then again, there is another quantum state which can interact with Bob's state, right? And therefore, when Bob measures on his particle, one of his particles, because it has interacted with some other state, he's able to capture some information about the other state or the interaction. And if he retains this interaction, then it becomes quantum memory for him. Right? So pictorially or in a way of a cartoon illustration, so this is some kind of an uncertainty game. And how does it proceed? So Bob, this is one. So Bob sends a particle to Alice, which may in general be entangled with his quantum memory, right? As I said, quantum memory in this sense. And Alice measures. So Alice, its particle is Alice gets. Now Alice has, in the simplest case, two choices of measurements of two complementary observables labeled by R and S. And she measures one of them, and she notes her outcome, and then Alice announces the choice of her measurement setting, whether she's measuring R or measuring S. Of course, not the outcome. Now, the game is such that just by knowing Alice's choice of measurement settings, Bob has to infer the state of Alice's particle, right? So again, we are getting to some inferred relations, right? Because these are two complementary observables, their uncertainty is maximum. So Bob cannot pinpoint with certainty what measurement Alice has done, what outcome she has. But with the help of his memory, he can do much better. Okay. So how better can he do? So he can, in fact, he can put an upper bound to the, he can put a lower bound to this uncertainty. So as we showed, in fact, in this work, again in 2013, that this is again some uncertainty relation that you appreciate. Now, if you apply the Heisenberg uncertainty relation, you get a bound which is much below, all in Nature Physics in 2012. Later on, what we showed that we took this fine-grained uncertainty relation, the paper of Oppenheim and Weiner, the science work, and we showed that now if we quantify uncertainty in terms of probability in a fine-grained way, not in any coarse-grained way, like, for example, using entropic uncertainty or Heisenberg uncertainty relation, you leave this bound. And not only that, what does this bound signify? This bound signifies that in any given physical situation, you cannot get better than that. So this is the optimal possible bound that you can have on reduction of uncertainty using something called quantum memory, right? So this is an application of uncertainty relation, fine-grained uncertainty relation, and as an immediate consequence, you can also, this comes in the security of quantum key distribution. By the way, Pankaj, please warn me 5 minutes before the talk. So because otherwise I can go on and go on. So this has applications. But before going to the applications, let me just tell you something that all of these seems to be some nice little theory, but physics is after all an experimental science. So whatever I have said, so does this have any kind of experimental evaluation? The answer is of course yes. Several people have done experiments. We are theorists, but we have collaborators, and there are others also. So for example, this is a Chinese group who tested our finite uncertainty relation in the presence of quantum memory. And this was done almost 5 or 6 years after our paper. And this indeed, they could verify that such reduction of quantum uncertainty in the presence of quantum memory happens, as showed by us in the context of the fine-grained uncertainty relation. And this is not the only one. There are other examples also. Okay. So now let me come to this part on, where am I? Yeah. So as I said, as I mentioned, that this have applications in the security of quantum key distribution. So how is it related? So again, in a nutshell, I mean, quantum key generation, all of you know. So here, security is provided by not on the fact that computation is difficult, like all classical security. How is classical security done? RSA encryption, all of you should know that. I mean, we all use keywords for our computers and everything. But if you have, in principle, a very powerful computer, you can hack all those keys. So on the fact that computation is a very resourceful thing. It requires a lot of, I mean, effort. But on the other hand, in quantum mechanics, right? And what is that? That is that in order to ascertain anything quantum mechanically, you need to impart a disturbance on the state. And the disturbance modifies the quantum state. So the people who are sharing such a code or such a key will get to know whether there is some hacker or not. So therefore, it is more fundamental, right? So this is what quantum security is all about. And so suppose now we consider some secret key protocol between two parties, Alice and Bob, and there is some eavesdropper or hacker attack and knows about this. Okay. By her very action, she disturbs the state and she gathers some information. So therefore, the quantity of secret key that is being transmitted between these two trusted parties is given by the difference of these mutual information, right? Mutual information, first of all, between Alice and Bob minus what Charlie or Eve is able to take away by her own measurement, right? So this is the secure secret key rate, and this is bounded. Okay, so this is lower bounded by the difference of these two mutual informations. And now it immediately brings us to our work. So what I promised that. So in these kinds of things, of course, we are using not only the application of Heisenberg uncertainty, but the application of something more refined, that is the fine grained uncertainty relation. Okay, or in the sense we can do it even with the sum uncertainty relation, right? So quantum steering or violation of the EPR paradox, so on and so forth, are all manifestations of uncertainty relations. And because uncertainty provides you this quantum security at the fundamental level, so we can know how much secure our key is. In other words, what is the bound on secure key transmission. So we can immediately apply these formulations and we get measures on the secret key rate. And as you see, in this case, this is using fine grained steering. So this K measures the violation of the fine grained steering inequality. Again, violation in terms of inferred observables. Let me again warn you very carefully. In nature, there is absolutely no physical violation of any uncertainty relation, but is inferred knowledge. Okay. So this key rate is again quantified by this magnitude of violation. Exactly the similar happens for the sum uncertainty relation. This is the violation. Delta signifies the violation of the sum uncertainty relation, and your secure key rate depends on that. Okay. So as I said that there have been several experimental implementations of fine grained steering. So this is another group. Actually, my next student Tanumay went to work in this laboratory in Paris, and using our idea, they did this experiment, which is detect steerability in. So which was beauty about Chinese groups is that they are so fast that by the time our paper is accepted, they already start the experiment and they can do things very quickly. And say they again implemented this demonstration of fine grained steering for 2-qubit mixed state. So I'm giving you 2 examples. So all of these have been tested in labs. Okay. Okay. So the last part of my talk, I think, how much time do I have? 3 or 4 minutes? 5 minutes. Okay. So last part of my talk, I would move to something again relatively very new, and that is another side of application of uncertainty relations. And here, to begin with, what is the perspective? We will begin by asking this question. Okay, so in quantum mechanics, as I said in the beginning, there are some very beautiful properties like uncertainty relations, superposition, quantum entanglement, so on and so forth, which have led to performance or demonstration of many wonderfully new tasks like teleportation and promise for implementing revolutionary technologies like computation, so on and so forth. But can somebody tell me or tell anybody that if there is one particular element in quantum theory that sets it apart from classical physics, what is that? So in other words, what is the fundamental or key feature or property of quantum mechanics that sets it distinctly apart from classical physics, which in principle allows beautiful information processing? Is the answer entanglement? Of course, many people will immediately say it is entanglement. But we know for sure that there are certain tasks which can be even done without entanglement. Okay, for example, Professor Bhupendev will say quantum computation can be done with states without any quantum entanglement. And there are other tasks I will also show you. So entanglement is very beautiful, but this is not the only thing which sets quantum mechanics apart from classical physics. But what we claim, okay, here is that if there is one thing, it is to do with the character of measurements or the character of quantum measurement, which is distinctly lacking in classical theory. And there is something called incompatibility of joint measurements in quantum mechanics, again a manifestation of the uncertainty principle. If there is no uncertainty principle, there is no incompatibility, right? So I now return back to the original spirit of the uncertainty principle, which was stated by Heisenberg. So if you are trying to measure joint observables, you cannot measure with perfect precision both, right? So this refers to the incompatibility of joint measurement, and something which is related is contextuality. Right. So to just motivate it further, I mean, quantum entanglement is indeed a powerful resource, but there exist many tasks like competition, also communication tasks, which happen without entanglement. And what we typically call them is prepare and measure scenarios. For example, again, I would say quantum key distribution. What was the original protocol of QKD? Okay, some of you must know it. It is the so-called Bennett-Brassard protocol given by Bennett and Brassard, and there is no entanglement, right? So it relies on superposition. So it calls such scenarios as prepare and measure scenarios. One of the parties exist here, and then they prepare a certain quantum state and send it to another party, and the other party, who is separated in time with the original party, measures that state. So this is not any special kind of responsible for entanglement or EPR paradox, etc., but this is a temporal correlation. You can regard it in a sense as temporal quantum correlation. So on a given quantum state, if you measure at time t1 and somebody else measures at time t2, or you can also measure at time t2, there will be some correlation ingrained between these two measurement outcomes. Okay, and another primary example of, success of such temporal correlations is something called so-called quantum random access codes, which are demonstration of non-classical temporal correlation. So there is an equivalence. Again, we showed it. So let me not go into the details, but this is 2 or 3 years ago. Now, then the question one asks, again, to make our earlier question more precise, that there indeed exists communication tasks without entanglement, but what causes quantum advantage in those communication tasks? The answer, as I said, to repeat, it is nothing but measurement incompatibility and or quantum contextuality, which is ingrained in the character of quantum measurements. Okay. So is it okay? Now it is come here. Okay. So what are incompatible measurements? Again, to repeat, so these cannot be performed simultaneously on a single copy of a quantum system, that is position and momentum, with any arbitrary precision. Okay. That measurement incompatibility is indeed the thing which discriminates quantics from classic people around the world. So what is the claim? Quantum measurement incompatibility is at the root of fundamental quantum aspects. Everything, for example, Bell non-locality, EPR steering, quantum contextuality, quantum violation of macro realism, temporal steering, anything you demonstrate, any beautiful task you achieve in the lab, you gain some beautiful technology, but all of it arises due to measurement incompatibility. Whether you have entangled states or you don't have entangled states, it doesn't matter. Okay. So character of quantum measurements and measurement incompatibility. So therefore, in order to actually, advocate our cause, we wrote a paper in 2023. So which says that there is a two-way relation between quantum incompatibility and advantage in quantum correlations. And so again, we typically consider this prepare and measure scenario. And what is more interesting, those of you who are a little bit mathematically inclined, we could exactly classify the states. I mean, which states are classical, which states are due to compatible quantum measurements, that is QD equal to classical, which states are to do with compatible measurements in the absence of local resources, and so so forth. Shared random, right? So now I would come to the last part of my talk. This is just a slide scenarios where we have quantum communication without entanglement. Okay. And there indeed the contextuality. So I mean, what is the? I mean, why are we interested? Okay. As we know, those of you who have studied quantum mechanics know that there indeed exists some correlations for where there is no probability distribution, which is in agreement with marginal distribution corresponding to the sets of compatible, jointly measurable observables. Okay. So suppose you have a collection of observables, okay, a set of observables, and you take a marginal of that, you trace out over one, okay, then you are left with a marginal distribution. Now the point is that in the end, after all, what matters is the probability distribution. But for certain correlations, there can be no compatible observables corresponding to these marginals, okay. So this, I mean, relates or gives rise to the study of something very beautiful, which is quantum contextuality. By the way, contextuality is an idea which predates quantum mechanics. Contextuality is what? So any physical object can have two types of properties. One of them is the so-called attributive property. So it is a property of an object which is constant, irrespective of observations or measurements. So for example, the rest mass of a fundamental particle, electric charge of a fundamental particle. However you measure it, okay, it doesn't matter. On the other hand, there are certain other properties of fundamental objects which entirely depend on the context. Okay. So for example, they are determined by the interaction of the object with the measurement apparatus or the external world. And as I said, that something like probability, something like spin of an elementary particle is entirely dependent on that. Which direction you are measuring, what kind of measurement you are using. So these are called contextual observables. And contextuality has many beautiful applications. As I said, that this is, I've listed several such applications: quantum state discrimination, self-testing computation. And by the way, those of you who are interested in computation must have heard about this work. I mean, several years ago, it appeared in Nature, and these people, the authors, showed that again, nothing to do with entanglement, but it is quantum contextuality which supplies the quote-unquote magic behind quantum computation. Without contextuality, there could be no advantage in quantum computation, so on and so forth. Okay, there are many advantages. Now, where we get in again a paper last year, what we showed that this is not only true in computation, but even in communication, and especially communication without entanglement. Also in communication with entanglement, it is contextuality which provides advantage. And not only that, there is a quantitative link up. Okay. So it provides communication complexity advantage. Okay. So we prove a two-way relation that wherever there is a system which has contextuality, it is useful for a communication task, which is which is advantageous over a similar classical task, right? And there is a two-way relation, and therefore what happens is that as the number of inputs grows, you have more and more such advantage. So this measures something called communication complexities, and without going into some further details, you can just read from these numbers. So these are something called state independent witnesses of contextuality, and as you say, you increase these dimensions, the difference between classical and quantum. Okay, how many resources you need classically to simulate the same thing? Okay, magnifies. So this order, 10 to the 13, 7, 18, 14. So the message is that contextuality again arises from the uncertainty relation. There can be no contextuality without uncertainty, right? And so therefore, again, this applies. We of course we did not use the same. Title as the Nature paper, but people would have said that we are plagiarists. But in fact, it is the same thing which is happening in the communication aspect as well. What those people showed, Howard showed in case of computation. So that brings me to the end of my talk. So I would like to summarize what we have discussed so far. So again, to repeat that most of us are only aware of textbook level quantum mechanics. It's quite natural in the sense that we are only aware of Heisenberg type uncertainty relation. Because in most applications in physics, Heisenberg uncertainty relation suffices. But starting from the early forefathers, Heisenberg, Robertson, Schrodinger, so on and so forth, in the last century, people have realized limitations of Heisenberg uncertainty relation, both from a foundational point of view as well as from the point of view of applications. And people therefore have devised or formulated better and better uncertainty relations, variance-based uncertainty relations, entropic relations, fine-grained uncertainty relations, and each has a particular niche, particular advantage. And as I could highlight, for example, there are advantages in, for example, bounds of uncertainty, in quantum correlation, the relations with non-locality, so on and so forth. And in this particular talk, I could only show you a subset of such applications. For example, determination of purity or mixed settings of states. I mean, this is all related to work which we have done. Demonstration of EPR paradox and steering. Then another beautiful application which I could just show a glimpse to you is the reduction of uncertainty using quantum memory. The original work was the of nature physics by Bhatta et al. And then if we apply the fine graining, which was proposed in this science paper in 2010, into this framework of quantum memory, then we could obtain precise optimal lower bounds of uncertainty in the presence of quantum memory. This was our work in uh, in 2013. And this is, of course, fine graining is related to non-locality, as we could also show in various works. Now, all of these have applications in the privacy of quantum key distribution that I also showed you a glimpse. So the better and better, more refined way of application of uncertainty leads to more refined secure key rates, right? That I showed you. And finally, towards the end, we took a strong stand that even with or without entanglement, you can forget about entanglement, you can consider scenarios where there is no entanglement, or even with entanglement, what is the precise one thing which leads to departure from classical theory or which leads to quantum advantage in information theoretic tasks, and that is nothing but measurement incompatibility and its cousin, which is this called so-called contextuality. And this leads to advantage in communication without entanglement, communication complexity, so on and so forth. So thank you very much, and I'll be happy to have questions. Yes, in the sense that as a concept. No, as a concept, because whenever people, of course, I mean, in the classical sense, for example, you can take the color of a chameleon. So sometimes it is green, sometimes it is red. So in a very heuristic sense. But of course, in a mathematical sense, of course, it comes after quantum mechanics when people at least knew they are, or maybe when people knew that there is rest mass, something fundamental as rest mass or charge, but other things which depend on, say, your orientation, for example. So in that sense, so they take it as a loose statement. It is not a very concrete one. Yeah.
Okay. What is actually meant by fine graining? Can you explain that?
Yeah. So fine graining is that the way we are actually measuring uncertainty prior to fine graining is something coarse graining, like we take an expectation value, for example, okay, on a given state. And then how do you measure an expectation value? You take all possible, there can be many, eigenvalues or eigenstates of a system. You combine them, average over them, and get an expectation value. So in this sense, it represents coarse graining. But instead of doing that, if you take one particular outcome, or maybe a combination of a few outcomes, and you measure probabilities, okay, instead of taking expectation value, so then it represents the uncertainty for that particular measurement outcome. Okay. So therefore, now you can use it. So you can use this very same probability precisely to quantify uncertainty as a physical characteristic of a given quantum process. So that in sense is fine graining. And the advantage is it leads to better and better. It leads to a true reflection of the non-local character of quantum theory, as these people showed in the science paper in 2010. Because if you take into account fine graining, that will give you the precise magnitude of quantum non-locality. For instance, as quantified by the violation of Bell-type inequalities for those situations. So if you take any other kind of uncertainty relation, you will not get a precise quantification of such quantum non-locality.
Okay, thank you.
There's two questions there.
What is a quantum memory?
What is a quantum memory? Okay, I mean, in a simple language, you can understand that suppose you have two particles which have interacted, say one particle here, they are here. So, and one particle, two particles are with me and they have interacted. Now I give one particle to you, right? Okay. So now, because these two particles have interacted, I have some kind of knowledge of the particle that I send you. And this is my quantum memory of the quantum state that is with you. Okay. And this can be helpful in various tasks because because they've interacted, correlations have been brought about. That is the whole spirit of the work of Einstein, Podolsky, Rosen, and quantum non-locality, starting from earlier days. So, because of quantum correlations, there is something which called quantum memory, which is knowledge or partial knowledge of the state of the quantum system, which is reflected in one of its partial components. Am I making sense? Clear?
Like, does it also allow you to store the amplitude
Yes.
of a quantum state?
Store what?
The amplitudes of a
No. Information about a quantum. Amplitude is a very general word. Okay, amplitude is is a property of a process. Okay, so but I would rather the more better way of saying is information contained in that state. So that memory can be stored. Okay, till the time your other factors destroy it, like environmental reactions or measurements, etc.
So, sir, so you talked about that there can be communication protocols without entanglement, but are communication protocols with entanglement or device independent QKD or whatever, they are generally more secure, right?
Yeah, of course. You're absolutely right. So when you want to do device independent QKD, then what is device independence? How is it shown? It is shown through violations of Bell non-locality. And violation of Bell non-locality can happen whenever, of course, there has to be an entangled state or correlated state, and that has to do with entanglement. So in that sense, security, that kind of security, device independent security, comes due to application of spatial correlation or entanglement. Right. But again, Bell inequality can be understood again in terms of contextuality. That is also true because if you have a single particle which has a contextual behavior and you entangle that particle with another one and you write down the Bell inequality, it can be proven as these people have done. In fact, one of the slides which I showed you, the definition of contextuality, it's not changing. Anyway, the same person, Kupczynski, who I showed you, the slide I showed you, took from him, he was the first to show that the derivation of Bell inequality, which is behind device independent security, comes through application of contextuality. Right. So it doesn't contradict what I'm saying, but how to reveal this device independence directly comes from the fact that you are violating a Bell type inequality, and that is only possible when you have an entangled pair of state. Does it answer your question?
Wondering when we are not using entanglement or like BB84.
Yes, BB84 never use entanglement.
But in that kind of.
Of course, yeah. But you have to weigh in two different things. You can make your protocol as secure as you like in principle, but in practice, when you are trying to set up a key between two distant locations, can you imagine how difficult it is to share an entangled state between two far locations. And not only that, to preserve it. How much resources you need. Extremely difficult. So you have to compromise. In principle, of course, device independence is perfectly fine. I mean, it is secure against all attacks, except for attacks using quantum computers. But let us not get into it. But at least it is secure against all other kinds of attacks. But the resources you have to spend in generating so many entangled pairs and spreading them apart at distant locations and preserving their correlations, not only against adversaries, but also against the influence of an environment, is much higher than what is required to just transmit one particle, like in BB84. What happens? In a superposed state, you transfer another particle, no entanglement. So I'm not saying one is intrinsically better or worse than the other, but there are two different things which have different uses in different contexts.
Actually, I have a question. So you have mentioned about that that Laguerre Gaussian beams of angular momentum entanglement. Is it the circularly polarized entanglement?
Okay, that is a good question. At the moment, it has gone away from. You cannot immediately answer you. But no, what are you trying to say? Is it only due to no? Are you saying that it is only due to circularized polarized states?
No, like we are.
No,
Like,
what does polarization has to do with it? I mean, these are essentially they are. I mean, if you look into it from another sense, they are states of the two-dimensional harmonic oscillator. So if you look into the first Laguerre Gaussian that I wrote down for you as 01, this is the ground state of a two-dimensional harmonic oscillator.
okay.
Right? So where does polarization come into it?
In polarization, we make it like HH, BB, HB, VH entangled.
No, no.
state.
That
So
is
like
no. That is polarized entanglement. That is polarization entanglement of two different, say, photons. That is fine, but this is entanglement in angular momentum. So this is nothing to do with polarization. Huh? Orbital angular momentum.
Okay.
So this is not polarization entanglement at all.
Okay. Thank you.
So you mentioned the measurement incompatible.
Yes.
So I mean, you mean by that two observables you are measuring which don't commute, or you mean something else?
Yeah. So essentially, they don't commute. I mean, basically means that if you have a commuting set of observables, there is no incompatibility. But you are saying taking a simplest situation where there are only two observables. Suppose there is a collection of observables. Okay. So A can commute with B, A may or may not commute with C, and similarly C with B, so on and so on.
This is a different way of saying things.
Yeah. This way of saying, that's why I said it is an application of uncertainty relation. Of course, somebody can ask me a little bit of sarcasm that, after all, is there anything in quantum mechanics which is not shown by uncertainty relation? Of course, answer is certainly true. Everything in quantum mechanics follows from uncertainty relation. But due to some bias, I mean, in my taste or the work I've done, I've given you examples of some information theoretic applications which are directly linked to various versions of uncertainty relation.
So, but this uncertainty, I mean, as you were saying, it should be perhaps the other way, incompatibility of the measurements of two non-commuting operators. This leads to Heisenberg. Right? Rather than
Yes, no, no. You see, this debate is very old. I mean, in quantum mechanics, is it an axiomatic theory or can you derive it from some physical principle? So this is a very old debate, and so far people haven't been able to completely derive quantum mechanics from physical principles. You are aware of all these works. So therefore people say, I mean, regards till now that it is a complete picture. Start from the postulates and get the physical aspect.
I didn't follow.
Things.
But what you are calling Heisenberg effect, as you were mentioning the very big, that is more like measurement.
Yes, original spirit of Heisenberg was measurement.
But what we call now Heisenberg, that is actually Robertson.
Robert, yes. Yeah.
Derived by Robert.
It was derived by Rob. Of course, you are right. So the details I couldn't mention because of lack of time. So I mean, the spirit of Heisenberg was to do with measurement, but later on the work went along in terms of preparation uncertainty, and there have been lots of work on preparation uncertainty, and all these versions like entropic relations and so on and so forth, fine grain, all have to do with preparation uncertainty.
But there are some measurements.
Yes. The group, the famous Ozawa et al. Yeah. So those things are also, so those I have not talked about so far. So there must be some, but at the moment I am not aware, or maybe I have not worked directly on those quote unquote measurement based uncertainty relations in information processing. But from a different argument, you can argue that this measurement incompatibility and contextuality are in some sense, I mean, applications of, maybe not in those direct forms as written by Ozawa, but they have to do with measurement uncertainty.
But here there is, when you have preparation, there is no measurement.
Preparation, there is no
No
measurement.
uncertainty due to me.
No uncertainty due to measure. It is inherently linked to the structure of the quantum state.
So these two are independent.
Yes, you can argue like that. I mean, though mathematically they may appear similar, but one is the inherent uncertainty linked to the character of a quantum state.
And that is measurement process.
Measurement problem is, of course, there. Yeah.
Okay. Anyway, so anybody else just to ask? Because the uncertainty relation you learn when you, but still there is so much there. Okay, then so let's think about it.
Okay.